Hi everyone, welcome to This Week in Space Science. I'm Michael Baltimore, and I am here with the director of the Coca-Cola Space Science Center, Dr. Sean Cruzen, each week here on Columbus State University Television. Sean, welcome to Twiss.
Thanks, Mike. Good to be here again.
It's a wonderful opportunity for us to learn more about space science, and you do bring us a lot of great information each week and do a wonderful job for us.
Well, thank you. I appreciate that.
And we're broadcasting out to our MediaCom channels, 98 and 99. We're on the Roku. We're at CSU.TV, ColumbusState.TV, and on iTunes. So we want to welcome everyone to tune into this broadcast. And
we're everywhere.
We're all over the place, and we're happy that you've joined us. So today we're going to talk about space science, of course, and you've got a couple of announcements. There are two big occurrences that have happened here. So we're going to jump right into the show. Tell us, lead us off. What did you find out about astrophysics this week?
Well, yeah, so that's a good way to put it. So, there's a lot of interesting things that I try to bring to the show from both the world of aeronautics and astronautics, some kind of planetary astronomy in the solar system and things like that. We occasionally jump into the deeper ends of the pool. We talk about more astrophysical topics. We talk about processes, astrophysical processes in the universe and how those processes are detected. And we try to piece the show together by reviewing all the newest things that are happening in all those areas. But this is the deep end of the pool. I will just tell you right now. So
there we go.
This is theoretical cosmology meeting observational cosmology.
Okay, I'm ready.
We have to even start by defining the word cosmology.
We may need to.
I'm not saying cosmetology. It's not the same word. So
no, that's right.
Cosmology is literally, in astronomy, it's the study of everything. And when we talk about cosmological models for the universe, we're talking about models that tell us how everything came to be and how everything got going. So it really is the deepest of topics. And in order to really understand those, we have to discuss, at least on a fundamental level, some of the principles of the two biggest theories on which physics operates at two very distant scales. One of those is everything on the biggest scale, and primarily we're talking about the theory of gravity then at that point, and we call that general relativity. And then we have to talk about the theory on the smallest scale, which has to do with particle physics.
Right.
And the dominant model under which we discuss particle physics is quantum mechanics.
Right.
And the interesting thing about those two gargantuan theories, general relativity devised by Einstein, quantum mechanics, which was devised by a whole bunch of different scientists. Einstein wasn't always on board with all the principles of quantum mechanics. It's interesting that that's true because even still today, modern physicists have not been able to justify with each other those two theories that describe our understanding of the universe on those two very different scales, the very biggest scale and the very smallest scale. So it's kind of an interesting juxtaposition, these two models that we can't quite totally unify, and it would be very interesting to do so. Right. But then now we're going to apply both of those simultaneously and try to come up with a description of the universe as we see it, and a very interesting development that we've seen. So that's the direction we're heading in for today's show.
Okay, because I looked at the list of things. We are covering so many things. You might say A to Z, but even more than that, probably.
We'll cover them a mile wide and an inch deep.
Okay, we're gonna hit the highlights of some of this very important kind of information. So you talked about two events. You called it the Holy Grails.
Yeah, these two discoveries are really considered both holy grails for verifying two fundamental occurrences within two very different aspects of our understanding of the universe. First is this period of time called the inflationary period of the universe, where things expanded very rapidly. The second is the existence of these weird things called gravitational waves. And gravitational waves have been postulated but never measured. So what if we could nail a measurement that both verified this weird inflationary era in the universe and also verified the existence of gravitational waves? Well, that's what appears to have happened. And so what I'd like to do is kind of build the story so we can talk about those two holy grails of astronomy being verified, and I'd like to tell our audience how we got to that point.
Okay.
Okay.
All right,
so
let's get started.
So before we jump into that, to those very deep cosmological ideas, we have to talk a little bit about the fundamentals of what we understand about our universe and the way it appears and the way we extrapolate that backwards in time. So the first thing I want to talk about is this really unusual circumstance that was discovered in the late 1800s and the early part of the 1900s, verified that all of the galaxies in the universe seem to be receding. They seem to be moving away from us. In other words, they're experiencing something that we call a redshift in astrophysics. And so I've got a beautiful shot of just a tapestry of galaxies out there. And here's the photograph right here. This is, of course, we've talked about this on other shows. This is what is known as the Hubble Ultra Deep Field. This is basically taking the Hubble Space Telescope and pointing at a blank part of the sky and photographing that blank part of the sky for a very long time. And what you see is you see this just beautiful tapestry of distant galaxies out there, as far literally as the Hubble eye can see.
Not blank at all, by the way.
No. When we said that this area of the sky was blank, we mean in terms of bright objects that can be seen with other telescopes. But this is the Hubble looking as deep as any telescope possibly can. And where we thought there was nothing, of course, there's not nothing. There is this incredibly complex network of distant galaxies. And so these distant galaxies, the interesting thing about them is if we look at the light coming from those galaxies, right, they demonstrate this pattern of light that we call a redshift, which we know from the Doppler effect in physics means that those galaxies are moving away from us. And something very interesting that a very famous astronomer called Edwin Hubble discovered is the further the galaxies are away, the faster away that they're moving. And so this is something very unusual. The further a galaxy is away, the faster its recessional velocity is. And so that leads us to think, and that led Hubble to think, that in fact all of that recession of galaxies is caused by the universe itself expanding. Now here's where I'll tell you a little story, and an interesting way to think about the universe itself. Imagine if we were up on a Saturday morning, Mike, and you and me, and we were hungry, and we were going to make something for breakfast, and we decided we were going to make some raisin toast. Okay. We wanted some raisin toast for breakfast.
That's an excellent choice.
Sounds good, doesn't it?
Yeah, sure
and so the first thing you have to do is you have to have some raisin bread. Well, we don't have any of that.
Okay.
So we want to bake some raisin bread. So we take a batch of raisins.
But yes,
it's a little bit more complicated, but you and I have kitchen skills. We can make this happen. So what we're going to do is we're going to take all of the ingredients to bake some raisin bread, and then when we get it out of the oven, we're going to slice it up and put it in the toaster, and we'll end up with raisin toast.
All right, sounds like a plan.
So what do we need? Well, we need some raisins.
Yep.
We need the ingredients that makes the dough. So we're going to need flour and sugar and salt and yeast, and that kind of thing. And so then we build this ball of raisin bread dough, and we're going to let it rise. And so for a period of time, this raisin bread dough will expand.
Sure.
All right. Now here's the thing to think about, and here's where the analogy gets more interesting. Imagine the raisins in that dough to be the individual galaxies in our universe.
Okay. That is a leap a little bit.
It is a little bit of a leap, right?
All right.
And imagine we have these special powers where we can actually see through the dough. The dough is transparent.
Okay. All right.
So as our raisin dough is rising because of the yeast that we put in it, as that raisin dough is rising, all of the raisins are moving away from each other.
Sure.
Why are they moving away from each other? Well, because it's the dough that's expanding, right? Because it has this yeast in it. So to complete the analogy, the raisins are like the galaxies or groups of galaxies out there in the universe. Yeah. And they're all moving away from each other. Well, we live on one of those galaxies.
Absolutely.
We live on a raisin, right? So we're on one of those raisins, and we're able to see through this transparent dough. So we can see all these other raisins out there, and we see this. We look over there, there's a raisin, it's moving away. We look down there, there's a raisin, it's moving away. And we suddenly come to the very sensible conclusion that we are the center of the universe because all these raisins are moving away from us. So we must be at the special place. We're at the special place, right? The middle.
Yeah, I think we tried that with the sun and the planets.
Yeah, it didn't work well back then either, did it?
In the centuries.
Because here's the thing. If we jump to another raisin, we would see the same thing. So from any raisin within the dough, except if you're right at the edges, and we're not going to go that far with our analogy, but if for any raisin within the dough, we would see all of the other raisins moving away from us because all of the raisins are moving because the dough's expanding. Well, the analogy is the raisins are the galaxies, The dough is the fabric of space, or space-time, as Einstein described it.
Okay.
And so the fabric of space-time is doing this expanding. And as it expands, these galaxies get further away. And from any given galaxy in our universe, we see the other galaxies receding or moving away from us, and we measure that in terms of a redshift because of the Doppler effect. So that's why we think that all of the galaxies are moving away. Well, okay, that's moving forward in time.
Okay.
But what if we could push the pause button and then the rewind button, and we could watch in reverse? All of the galaxies would be coming together.
Sooner or later, they're going to come into one spot,
Exactly.
one space.
So
right,
if we
okay.
run time backwards, you
Yes.
see exactly what you just described. All of the galaxies coming back together. It would look like an inversion of that recessional velocity. It would look like not a recessional, I don't know. It's a coming together velocity. They're all coming together. Anyway,
Right.
So as the universe is moving together and all these galaxies are moving together, it's like a gas that's being condensed. And so a gas being condensed, the temperature will rise. So if you squeeze a gas, the temperature gets hotter. So we see a universe that's getting hotter and hotter, smaller and smaller, hotter and hotter and smaller, until finally it's really, really tiny and extraordinarily hot. Let's hit the pause button again.
Okay.
Now let's play the video forward. You begin with something incredibly small, incredibly hot, and then all of a sudden it moves out and it cools off and all those pieces fly apart.
Yes.
That's the expanding universe. That's the model of the expanding universe. I think maybe we have an image here that kind of is a cartoon of that. And here you see our raisins and our transparent raisin dough right here.
Back
right?
to the raisin toast. Yeah, I'm beginning to understand.
There it is right there. So there are all those galaxies. You can see as the universe expands, the galaxies get farther apart. All the galaxies are moving away from each other. So any galaxy would see recessional velocities within the spectrum of the other galaxies by the Doppler effect. And so this is where this concept of the Big Bang theory was formed. And actually Fred Hoyle, a very famous astronomer, coined the term Big Bang to make fun of the idea. He said, "What do you mean? You mean everything started at a little dot and then there was some kind of big bang and then everything flew apart?" You know, so he didn't really like the idea. He was an advocate of this model called the steady state universe, which means everything has been the same, it's unchanging, and nothing's really being created or destroyed. It's all just kind of recycling, and it's a constant size, it's infinitely large. Well, that's not what our current model says. And so Fred Hoyle didn't like that new model, nicknamed it the Big Bang to make fun of it. It kind of stuck.
It did, didn't it?
So viewers, when you're out there and you hear the term Big Bang theory, it's really a description of the expansion of the universe out from a single point. And that's really what we're talking about, okay? So within that thing called the Big Bang theory,
yes,
we find that when we look out at the universe today, the universe is very, scientists use the word homogeneous. In other words, it's very uniform. It almost appears that everything's the same everywhere. And if we look that way and we look that way, as far as we can possibly look, everything's kind of at the same temperature. Well, the problem is that when we look this way as far as we can look, and we see objects over there, then we look the other way as far as we can look and we see objects over there, there's not been enough time since the beginning of the expansion of the universe for information from those most distant objects to reach those most distant objects. They're too far apart. The word is causally connected. They're not causally connected.
Right.
So why would they be at the same temperature? Well, they shouldn't be unless they were causally connected at some time. Well, if they were causally connected, in other words, if light could travel from one of those objects to the other in the age of the universe at one time, how come it can't now? That doesn't make any sense.
right.
So scientists have postulated this weird thing called the inflationary era of the universe. It's where the universe itself, in its expansion, expanded faster than the speed of light. Now, we know today that nothing can travel faster than the speed of light.
Can't do it, no.
So this was a time in the history of the universe where that particular law was violated. And if that law was violated in this way, it would leave a signature behind. There would have to be some evidence that that law was violated. And again, if you want the deep end of the story, you're going to need to get online and read a little bit more. I'm kind of glossing over some things, obviously, but that's what we're looking for. We're looking for some signature, some measurable evidence that yes, indeed, this weird inflationary period where everything expanded faster than the speed of light did in fact occur.
Okay.
And it turns out that we could find that signature from gravitational waves.
Yes, you mentioned gravitational waves. That's a new concept around here.
It's a strange concept. I'm going to come back to it because I'm going to tell you where we see it, but we are going to explore a little bit these weird gravitational waves, which are postulated again by Einstein and the theory of general relativity, and have never, ever, ever been measured.
Okay.
And scientists have been looking. In fact, very large facilities have been built looking for these gravitational waves, these ripples in space-time, and you're kind of seeing a graphic right there of what that might be like. What we're seeing right here is a pair of black holes that are orbiting each other, and those gravitational fields are so strong from those black holes that they're causing these ripples in space-time. And those should show up on our instruments. They just haven't been measured yet.
Okay.
So again, something that's been postulated but not confirmed by observation. And that makes observational scientists like myself a little nervous when theory is predicting something, but yet we can't quite measure it.
So get to it.
So let's talk about another idea quickly in this idea of the expanding universe, and that's this idea of the cosmic microwave background radiation. It turns out when that expanding universe was coming out of that really hot period, the early universe was so hot that normal matter could not exist. It had to cool, the universe had to cool down first. And right at the moment when the universe cooled down enough for normal matter to condense out of this field of really hot energy, then the moment that happened, mass separated from light, and then light was freed up to travel out through the universe. Well, then the universe cooled down even more. That light was then redshifted, as we've been talking about. And today, that thermal signature from the universe would be in about the 3-degree Kelvin range, which is extraordinarily cold. And that 3-degree light would be about microwaves. So this is a very interesting thing that was first measured by a group of scientists called the COBE team, Cosmic Microwave Background Explorer. It was a satellite. They were the first ones to measure this microwave residual radiation it's really a light signature verifying the occurrence of the Big Bang, verifying that radiation decoupling period in the expansion of the universe. The team won a Nobel Prize for that first observation of that microwave background radiation. And the map that you just saw on the screen there a minute ago, that was a much more detailed image of that microwave background radiation. And what you saw in that image, and maybe we can put it back up again, what you saw is you saw asymmetries. You see, it's bumpy. Now, it's not very bumpy. It's 1 part in 100,000 is what these variations are. But you can see, like a topographical map here is what we're looking at, of that microwave background radiation, or the thermal map of the universe. You see this little bumpiness. And it turns out that those tiny asymmetries in the early universe is what allowed matter to even clump together in galaxies today. So that was a very interesting result from the original measurements of that microwave background. It's one of the things that told us that yes, the Big Bang occurred, and yes, the asymmetries in the radiation field led to the kinds of structures we see in the universe today, which are things like galaxies. And inside galaxies are things like stars, and around stars are things like planets, and living on a planet is you, me, and all of our friends, and dogs and cats and trees and all that stuff. So that's how we get from those extremely esoteric bumpiness in the microwave background to right here at CSU TV and all the stuff that we know is normal matter around us.
Right, and we're measuring that radiation. That's one of the things that they're really measuring. And
exactly.
That differences in radiation across there. And that map, that graphic that we showed, that's the entire universe as we
It's really
know.
A map of the whole sky. And it's one of these, projections that's projected onto an oval. That's just to give you a way to look at it on some kind of a flat space. But if you can imagine that oval kind of wrapped around all around you, that's really a microwave map. A map in microwave radiation of the entire sky. And that little bumpiness is the signature of the discontinuities in that microwave background that led to the mass clumping together and forming galaxies and all the other stuff we talked about today.
All right, so
very interesting. Now that's a past result, but that's a very interesting thing to be able to understand about our understanding of the universe. We've come that far.
Sure, and that inflationary period that you talked about. But what caught my attention was this notion of gravitational waves, because again, that's a new term.
It is
for me here, certainly. So maybe some of those. But all right, go back there and kind of help us understand what that really means. You showed the graphic with the two black holes, kind of putting out, spinning, and showing those waves going out. What are gravitational waves?
Well, maybe we could put that graphic back up real quick. And so the idea is this. It's a basic idea about the theory of gravity. It comes from Einstein's theory of general relativity. And it basically says this: mass tells space how to behave. These are my own words.
Okay,
well, this is my own
good words.
Simple-minded interpretation of Einstein's theory of general relativity. Mass tells space how to behave, or more importantly, what shape to be in. So as we look at this graphic, we kind of laid a grid out over here, and this is a NASA image. It lays a grid out over the space-time, and it shows that these two black holes, as they orbit around each other, they make ripples along that grid. Well, Einstein defined this thing called a space-time manifold, and he really said space has a shape to it. It has a shape to it in 4 dimensions. We're picturing it in 3 dimensions on this graphic, but it has a shape. It has a shape in 4 dimensions. And when masses exist in that space-time manifold, they actually bend the space or warp the space-time. So in fact, what we experience as a gravitational field, like we're being drawn down to the Earth right now, is really because space-time itself is bent in such a way that we slide down this curved space toward the big mass of the Earth. The Earth slides down the curved space caused by the mass of the sun. And that's why we orbit it. The sun slides down the curved space caused by the greater mass of the galaxy, and that's why it behaves in the orbital manner that it does around the center of the Milky Way, and so on and so on.
So in short, I mean, that's why the planets are kind of on that plane and react to the gravity of the sun in our solar system, for example. And it's almost a fabric of space. I've heard that term
yes,
used
exactly.
as well.
And the analogy that goes along with that fabric of space, in a way that we can imagine it, is kind of, it's a 2-dimensional analogy. It's kind of a simple cartoon. Take a cannonball or a bowling ball or something very heavy and set it in the middle of a trampoline. The trampoline bends down.
Sure.
And then take another small ball like a ping pong ball and try to roll it in a straight line across that warped trampoline. Well, it would move along the curve caused by that heavy object in the middle. So the heavy object is like the sun, the ping pong ball is like the Earth, the trampoline itself is the space that's actually being warped, and the little ball rolls along the edge of that curved space, and that's what we call gravity, and the shape of that motion would be called an orbit at that point, right? So so you have to understand that to understand where we're going with this concept of gravity waves. So imagine then if some disturbance was occurring on that trampoline that had its basis in time. In other words, something that was repeating. Maybe you're thumping the cannonball in the middle of the trampoline every so often, or maybe you have 2 cannonballs that are orbiting around each other. That would cause the shape of the trampoline to vary in time and oscillate. Oscillate's a great word, exactly. So if the trampoline is oscillating, imagine the trampoline going on forever. If you were out somewhere in a very distant part of the trampoline, every once in a while you'd feel a little jostle, you'd feel a little bump, occurring on your space-time manifold. That's a gravitational wave. So that's a ripple sent out through the fabric of the space-time continuum by some massive objects behaving in a certain way.
Okay.
Interesting stuff. Well, one of the ideas behind the inflationary period is that there should have been all kinds of ripples that were sent out by the actual events that occurred during the inflationary period. And they would actually cause all sorts of ripples to propagate out through the universe and through that cosmic microwave background radiation that we saw.
Sure.
And those ripples then would cause a certain polarization of that light. Now, polarized light, if you ever had polarized sunglasses, when you look through polarized sunglasses, you see glare in one orientation and not in another. So polarization of light is something that we understand in daily life. But here, let me look again. So this is another graphic of the history of the universe. On the left is that event now known as the Big Bang, where it's shaped like a funnel and it gets wide really quickly. That's the inflationary period. If you look at the bottom scale, and maybe you have a little hard time reading this on this graphic, but it's the inflationary period occurred at 10 to the minus 32 seconds. So that's like a trillionth of a trillionth of a billionth of a second.
All right, I don't know that number, but that's a lot.
It's a decimal point with a whole lot of zeros, and it's a really small time. It's one of the smallest times that we can measure anything occurring in the history of the universe. That's when inflation occurred, and then the decoupling that led to the microwave background radiation, that occurred at about the universe only being about 300,000 years old, which is very, very young compared to the total age. We now think it's about 13.8 billion years old is how long ago that Big Bang occurred, and that's the age of the universe now. So all that business took place in the very, very early parts of the universe and the history of the universe, and that's one of the important things to understand. And those gravitational waves then would have caused ripples in that very early universe that we could now see as polarizations in that microwave background radiation. Well, there's a telescope in a very unusual place.
Okay.
It's near the South Pole.
That's where I was going, South Pole. I don't know why I thought about that.
Well, why would you think about that?
Maybe you mentioned it before the show, but still.
Why do we have a South Pole? Well, we have a South Pole because of rotation, but another way we can think about the South Pole is because of the magnetic field of the Earth. And it turns out that if you go down to the magnetic field of the Earth, where the magnetic field of the Earth comes to a South Pole, and you go down there where the atmosphere is a little bit different for a variety of reasons, you will find that microwaves actually get through the air a little better down there. And so if you want to observe the microwaves, which don't generally get through the atmosphere very well, that's why we're not cooked by the sun's microwave radiation emissions, by the way. You know what microwaves do to a hot dog? It's not pleasant, right?
Not good.
Our atmosphere shields us from most of that, which makes it hard to see microwaves from space unless you go to someplace like the South Pole.
Okay.
So they built a telescope near the South Pole. It's called BICEP-2. The acronym is Background Imaging of Cosmic Extragalactic Polarization. For some reason, I can't stuff all that in my head.
But that's easy for you to say, as the Ojo.
Background imaging of cosmic extragalactic polarization. It's a microwave telescope at the South Pole that looks like this.
Oh, there you go.
And so microwave telescopes don't exactly look like optical telescopes. They look more like these things called feeder horns, where you might see the phone company beaming signals with microwaves on a giant tower.
Right,
you might see horns that look something like these. And so these are giant feeder horns that are receiving microwaves from outer space. And the concept behind this telescope is to measure that polarization of the cosmic microwave background radiation to see if we can find the signature left over by the gravitational waves produced by the inflationary period of the universe. Wow, that was a lot of dots to connect.
That is a lot.
But
and
that's what these...
very, very small, too, so it's good luck with those guys down there. They're probably able to do some things or you wouldn't be reporting.
Well, exactly right. And in fact, they were very successful.
Okay, there you go.
A team led by scientists from the Harvard Center for Astrophysics, so they call it CFA, Center for Astrophysics, at the Harvard Smithsonian Institute. They were able to go down there, with other scientists from other institutions, by the way, use that telescope, make measurements. They were able to analyze the measurements, and they actually found the weird polarization that they were looking for that could only be caused by the inflationary universe. But the interesting thing about this is also the first ever observational confirmation of gravitational waves.
Okay.
So it's a two for one.
There we go. Yes.
Not only
Throw
did
in
they
gravitational waves.
exactly.
Yes.
Not only did their science verify, well, at least if it stands up. Now remember, I'm only reporting this about 5 days after it was first announced. All right. So if their observations hold up, not only were they able to verify inflation, but they were also able to have the first ever observational evidence of gravitational waves, all together in the same measurement. This is literally one of the biggest.
It's a big find.
The biggest finds in astrophysics ever, honestly. And in the last kind of paradigm shifting observation like this was really the observations that led us to think about this weird stuff called dark energy. So not since the announcements that led to the concept of dark energy have we seen a milestone set of observations like this one. So really, we've talked about all these convoluted, complex things. I've tried to present them in the simplest way I know how, but they do all lead to some really important astrophysics and some verification of some very fundamental models of our understanding of the universe, which is a really big thing. And so I think we have an image of the B mode polarization here. I want to show you just a little bit of what they found.
Yep.
There's a graphic here that shows this thing. So this is the polarizations that were first observed by this biceps instrument that led us to believe that we finally have, as a human race, some confirmation of gravitational waves and the inflationary period of the universe.
All right. We're going to need some scientists like you and some others to explain that to it. It looks a little bit like an abstract art.
It does look like abstract art. Look particularly for the little swirly curls that you see in this diagram. You see kind of some straight-on polarizations, but then you see some swirls. And then I want to go to my next graphic, and I will show this a little bit easier to understand. On the left-hand side, we see what's called the E mode polarizations. Don't worry about the letters. Don't get hung up on that.
All right.
We see some shape in the way the fields of light are traveling. The E mode on the left is a simple kind of pattern, and you probably saw some of those patterns in that other graphic as well. But those can be explained by things other than inflation. So it's the one on the right-hand side, the B mode polarization, where you see these polarization modes of light lining up in these patterns that almost look like they look like a sun. They look like a sundial. They look like a swirl, like a pinwheel. Mm-hmm. Exactly. So those pinwheel-shaped polarizations that are also seen in that previous image, those are the ones that are the B mode polarizations, which simply can't occur in the microwave background radiation without the influence of gravitational waves. It's like waves slapping up on the shore of a beach. And you might go out the next day when it's low tide, and you might be looking at the sand where no water's around, but you still see the pattern left over from the waves that were there the day before. Well, these are like the patterns in the sand that are left over from the actual gravitational waves caused by the inflationary period of the Big Bang model, right? So this is something that we can see today that's left over from some waves that were around a whole long time ago, and they left these patterns within that cosmic microwave background radiation, and we see them today, we observe them, and it's observational confirmation of both inflationary period and gravitational waves, if it holds up.
Right.
Now, mind you, it was published there's a very big asterisk there. It was published in the journal Nature, so scientists have peer-reviewed this, but obviously now that it's been released to the whole scientific community, lots of other scientists will be trying to make their stock and trade by disproving or changing these observations or something. And that's just the process of science. Sure. That's just the way science is a very organic kind of human endeavor, and so it takes lots of people to be able to do that. And so we talk about the scientific method. Within the scientific method is a verification of hypothesis by continual observations and experimentation. That's now the phase that we're in, right? So this is going to be scrutinized. It's going to be a lot of scientists are either going to be trying to confirm this or reject this based on their own observations. Once this has gone through that kind of threshing mill, if you will, of science, if it stands up, this will be one of the most important observations made to advance or to verify our understanding of the true intricate nature of the universe and that weird thing called the inflationary period where the whole universe expanded faster than the speed of light.
And gravitational waves.
And gravitational waves, exactly.
This has been an interesting show. I may have to rewind and watch this again just to kind of keep up with receding galaxies, expanding universe, Big Bang theory, gravitational waves, inflationary period, and the bicep 2 measurements at the South Pole.
Yeah. The one thing I would say, I love to point people toward good resources. There are now developing a whole lot of great internet websites that are discussing this. There are probably some bad ones out there discussing it too. So let me point you to a couple I know that are good ones.
Internet, right?
Space.com is one of the important ones, right? So go to space.com and type in bicep 2 or gravitational waves or inflationary period or any of those kinds of things. I think you'll find plenty of articles that are about this particular set of observations out there. Also, if you go type in the Center for Astrophysics, Harvard-Smithsonian Center for Astrophysics, type that into a search engine, you'll come up with some websites for those folks, and I know they'll have this story linked there as well. So go explore it a little bit more depth. this amazing result at those websites. It'll fill in a lot of the details that I simply don't have time to go through here on the show.
Sure.
And you will find some very interesting stuff about these amazing observations and amazing confirmed science now for inflationary theory, as well as the gravitational waves.
All right, that is good information. Thanks for those resources. We want our viewers to kind of follow up on this. You know, you tune in, you hear this thing, you want to learn more. We hope, anyway.
Yes, indeed.
So we're happy to have all this information and provide it for you right here on This Week in Space Science. I'm Michael Baltimore for Sean Cruzen. We'll see you next week on Twiss.